The universe is governed by four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each force operates over different scales, and each one plays a unique role in how matter behaves and interacts. At the very largest scales, those of planets or stars or galaxies, the force of gravity dominates. At the very smallest distances, the two nuclear forces hold sway. Between these extremes, electromagnetism rules. At the atomic scale, electromagnetism governs the interactions between atoms and molecules. It is the force that underlies the periodic table of elements, giving rise to all of chemistry and, through this, much of biology. It is the force which binds atoms together into solids and liquids. And it is the force which is responsible for the incredible range of properties that different materials exhibit. As if this wasn't enough, there is much more to the force of electromagnetism, for it is, quite literally, responsible for everything you've ever seen. It is the force that gives rise to light itself. From the soft glow of a candle to the radiant energy of the sun, it is electromagnetism that makes vision possible. Every color, every shadow, every visual experience is a manifestation of this fundamental force. Each particle in the universe carries with it a number of properties. These determine how the particle interacts with each of the four forces. For the force of gravity, this property is mass. For the force of electromagnetism, the property is called electric charge. Electric charge, a basic property of matter carried by some elementary particles that governs how the particles are affected by an electric or magnetic field. These fields exert influence on charged particles, resulting in observable effects. The force between stationary charges is called electrostatic force. The electrostatic force obeys Coulomb's law. Coulomb's law quantifies the electrostatic force between two particles by asserting that the force is proportional to the product of their charges, and inversely proportional to the square of the distance between them. Coulomb's law applies to elementary particles and small charged objects as long as their sizes are much less than the distance between them. It also applies to uniform spherical shells or spheres of charge. In that case, the distance between the centers of the spheres must be larger than the sum of the sphere radii. That is to say, the charge must be largely separated. These are typically called point particles. By point particle, we mean an object whose radius is very small compared to the distance between it and all other objects of interest. So we can treat the object as if all its charge and mass were concentrated at a single mathematical point. Small particles such as protons and electrons can almost always be considered to be point particles. For the purposes of this video, we can think of electric charge as represented by Q. Importantly, charge can be positive or negative. It can also be zero, in which case the particle is unaffected by the force of electromagnetism. An object with no net charge is referred to as electrically neutral. Like charges repel each other and unlike charges attract each other. Electric charge is carried by subatomic particles. As we consider electric and magnetic interactions in more depth, we will find that we need to consider the individual charged particles, electrons, and nuclei that make up ordinary matter. In ordinary matter, negative charge is carried by electrons, while positive charge is carried by protons in the nuclei of atoms. A piece of matter will have a negative charge if it has more electrons than protons, a positive charge if it has fewer, and be neutral if the numbers are equal. The unit of electric charge in the International System of Units is the coulomb, named after the French physicist Charles-Augustin de Coulomb. Charge is quantized, coming in integer multiples of discrete, indivisible small units called the elementary charge, denoted as E. The charge of a proton is positive E, and the charge of an electron is negative E. This quantization of charge implies that electric charge cannot be divided into smaller parts. Typically, a neutral atom, molecule, or macroscopic body acquires a net charge only through the gain or loss of electrons, each of which possesses a charge negative E. An uncharged object becomes negatively charged if it gains electrons and becomes positively charged if it loses electrons. All electrons carry the same quantity of charge. The more electrons an object gains or loses, the greater is the overall negative or positive charge upon it. In any isolated system, in any chemical or nuclear reaction, the net electric charge is constant. The algebraic sum of all the charges present in the system remains the same. Charge can neither be created nor destroyed. It can only be transferred from place to place, from one object to another. When a particle with charge positive E is created, a particle with charge negative E is created simultaneously. When a particle with charge positive E disappears, a particle with negative E also disappears. Hence, the net charge of the universe remains constant.